analyzer in this situation and to recognize how much this conjecture and his guidance in general has guided so much research. So let me, many of you here are experts, but let me start with just really the basic background for some students who might be connected. So the first point of view really is that if you have any kind of map, you can define for any initial condition, you can define this sequence of probability measures, mu n. And everyone who has worked in this field, this is very familiar, but I want to take just a few seconds to say how this particular formula, I think, is really amazing for me because it's a very simple concept. And this concept is really to start looking at an orbit or a finite piece of orbit as a measure. And it turns out that just this simple observation opens up incredible doors to so many problems and so many ideas and so much research. So this is a measure that describes a finite piece of orbit. And the obvious question then, as you increase n, so as you look at longer and longer pieces of orbit, what happens to this sequence of measures? Does the sequence converge? Does it not converge? If it converges, then that means there is some limit measure mu, which describes as a measure the distribution of this orbit, right? So if it does not converge, it's even more interesting in some sense, but I will not go into it now. Let me just say that the idea of convergence motivates the concept of the basin of a probability measure. So given a measure, you want to know what the set of points is for which this sequence, its orbit, in a measure theoretic sense converges to mu. Of course, if you choose a measure mu arbitrarily, there's no reason why this basin should be non-empty. Most of the times it will be empty. So there is some specific measures for which this may be non-empty. And in particular, we're interested in the measure in which this basin is large. So we're interested in measures that describe the asymptotic dynamics of a large set of points. And so this motivates the definition of a physical measure. So it's a physical measure if this basin has positive Lebesgue measure, where Lebesgue measure is the measure on the manifold, normalized measure on the manifold. So there are many simple examples where physical measures do not exist, such as the identity map, or many other examples in which they do not exist for more sophisticated reasons, more complex reasons. But there's also many situations in which they do. And if they exist, the physical measures, and if their basins cover the whole manifold, then in some sense, if we know these measures, we can say that we have described the dynamics to some extent from a measure theoretic point of view. So a natural question, which is really the main focus, I will not describe the technical description of Paley's conjecture, but the spirit of Paley's conjecture is that typical dynamical systems admit finitely many physical measures. So that if you take a typical system, then you almost every point will have one of just a finite number of options in terms of the statistical distribution. So the concept of typical requires some care about exactly what we mean by typical, but I'm not going to go into that now because that's not the focus of my talk. I want to focus here just for the moment on the spirit of the conjecture. And let me say that this conjecture, we're still very, very far from having any proof of this conjecture, although there's a lot of partial results. And I would like to propose a natural subdivision into two subconjectures. So we can divide this into two conjectures. So defining a category of systems which satisfy the conclusions of Paley's conjecture, and then naturally reduce the conjecture, then reduces to the fact that if we could prove that hyperbolic systems admit finitely many physical measures, then the conjecture would be reduced to the fact that typical dynamical systems are hyperbolic. So I will say in a second what I mean by hyperbolic. Let me say that for conjecture B is really the most difficult part. So conjecture B, we are a very long way from being anywhere close. On the other hand, for conjecture A, this is a conjecture that on which basically there has been work for about 50 years and or more, and there is considerable work, and we could say that essentially it is pretty much solved up to some detailed ways. So I want to describe some of the work in this direction. If anyone has any questions, I think they can ask me, right? In either in writing or in words. I'm not sure. Okay, so everything depends on the definition of a hyperbolic set. The definition is a little bit technical, but I do want to give it because everything hinges really on this definition. So in this context, the notion works for arbitrary maps, but we will stick to diffeomorphism in this case. And the results I will mention will be just for surface, for two-dimensional diffeomorphisms. And we say that an invariant set is hyperbolic. Yes. Is chi epsilon hyperbolic? So why is there these lines on this? Somehow there's some lines. Anyway. Okay. I don't know why there's these lines. So
you probably made them.
Exactly.
You have a point or
you need to annotate
a pen or something.
Okay. Thank you. Okay. So the definition of hyperbolic is fairly standard. I think most of you are familiar. But in this particular case, just there are many definitions, there are many slightly different definitions. So to make sure we're all on the same page, we have a measurable splitting that is invariant, preserved by the derivative. We have a measurable function on the set lambda, which is measurable, which means it does not really satisfy any continuity properties, but it has this very important property here in terms of how it varies along orbits. So if this is the x and this is f of x, epsilon is small. So what this is saying is that along an orbit, it varies in a controlled, slow way. And such that for all x and all unit vectors, we have two properties. We have that the angle between these two subspace of the decomposition is bounded below by this function c of x, and the derivative on unit vectors in the expanding and contracting directions satisfy asymptotically exponential behavior with exponent chi, but with a constant cx, right? So the key point here, and also in backward time, we have the same thing. Yeah. So the key point here, of course, is that this constant, this angle, is not bounded away from zero, because this constant can get arbitrarily small, it can vary and it can degenerate. So that's why in general the set is just measurable and not closed set. Just a couple of brief remarks. Sometimes people talk about non-zero Lyapunov exponents. So if you have a hyperbolic measure that has non-zero Lyapunov exponent, then the typical points for this measure have a chi epsilon hyperbolic for every epsilon. Of course, the function depends on epsilon. So this function c depends on epsilon. So if epsilon is very small, it means the variation is very small. And in some sense, in this definition, you can also take the case epsilon equals 0. Epsilon equals 0 means that here cf of x over c of x is equal to 1, which means that this constant can be chosen uniformly, which means that the angle is uniformly bounded away from 0. These constants are uniform in x, and this is the uniformly hyperbolic case.
Stefano?
Yes.
is chi a constant? Is chi the same for all orbits, or is chi also measurable?
No, in this particular setting, I'm assuming chi is fixed. So it's a chi epsilon hyperbolic set.
Okay, so it's more uniform.
I'm assuming that the exponent is bounded below. Yeah, I'm assuming the exponent is bounded from 0. So this, thank you, Keith. This is an example of how many different variations. So you can sometimes call a hyperbolic set, say, let's say, a countable union of chi hyperbolic sets in some sense, where you allow this chi to also be arbitrarily small. Right? So there's many different variations, and that's why the subject, often some of the results depend on exactly what definition we give. And we wanted to give this definition because it is fairly general, so it does not assume the Lyapunov exponents converge in any way. And also we do not assume that it's chi epsilon hyperbolic for every epsilon. So there is a really a key, there is a fairly explicit value of epsilon sufficiently small, which guarantees that stable and unstable manifolds exist. This is the Pessin theory, the classical Pessin theory. I think Yasha can confirm this for us. And this is really the epsilon that we want to choose. And so from now on, this will be the main assumption that we make. So that we have, from now on, I will just talk about a set being hyperbolic. And what I mean is that it's hyperbolic for some fixed chi and for some sufficiently small epsilon, such that the stable and unstable manifolds can be constructed at every point. So that's our definition. And we can use this to define the notion of hyperbolic diffeomorphism. This again is not a standard definition, but in this case, a natural way to define a hyperbolic diffeomorphism would be, for example, a diffeomorphism that where lambda is the whole manifold, modulo 1, or lambda, you have a hyperbolic set that has full measure. But this would exclude some special cases like attractors. So it seems more kind of natural to give the following definition, simply to say that a diffeomorphism is hyperbolic, or at least some part of the diffeomorphism is hyperbolic, if it admits a hyperbolic invariant set which is fat. And by fat, I simply mean that the union of the stable manifolds is 1, or is just positive. Okay, in fact, in our results, it would be sufficient for this to be just positive. But this allows for the set to be an attractor, so the set lambda itself to have 0 Lebesgue measure, but the stable manifolds to have positive Lebesgue measure. And this is kind of a reasonable definition for a hyperbolic diffeomorphism. So going back to conjecture A, that hyperbolic systems admit finitely many physical measures, Viana formulated a conjecture already more than 20 years ago, I think, which is a kind of, I consider, important first step in this direction, which is simply that hyperbolic systems admit at least one physical measure. And it turns out this is already challenging, and so we will concentrate on that. I will say something about the finiteness later on. So the Viana conjecture was motivated, of course, by existing work, and the first really pioneering work is that, as we all know, Sinai, Bowen, and Ruel in the 70s, where they proved that in the particular case of uniformly hyperbolic system, they indeed conjecture A holds for those maps. And let me say now what they did is they constructed, so Sinai, Ruel, and Bowen, when they did this, they constructed a particular kind of physical measure that is now called Sinai, Ruel, Bowen measure. The definition of SRB measures is usually fairly technical, but I think one advantage of having spent some time defining a fat hyperbolic invariant set is that you can actually give what I think is a perfectly equivalent definition, which is just that every set of positive measure is actually a fat hyperbolic invariant set. That So a Sinai-Llewellyn measure is conceptually a measure that lives on a hyperbolic set, on a fat hyperbolic set. So there have been a lot of partial results towards Vienna conjecture, because in the definition, there are various quantities. There is the angle, there is the unstable direction, there's the stable direction, and each of these can have some uniform, non-uniform estimates. So the definition I gave, everything is measurable, everything is non-uniform. The Sinai-Llewellyn discussed the other extreme in which everything is uniform and the splitting, the angle is bounded away from zero, and indeed is continuous. And then there have been several intermediate results that have relaxed some of these conditions. For example, initially first pioneering results relaxing just the stable direction is non-uniform. This goes back to a paper of Pessin and Sinai that was then further improved by Bonatti and Viana more recently. Then there's some works which are a bit more challenging where EU is non-uniform, but yes is uniform, and you still have a continuous splitting. These are Alves, Bonatti, and Viana was the first paper in this direction, and then more recently a paper by myself with Alves, Diaz, and Pinheiro. And then we have really the more general case where everything is non-uniform. So there is initially a paper of Kleimenhager and Dolgopiat and Pessin in which they considered this case, but they still had quite a few technical assumptions. And then recently two papers, so this paper of myself with von Kleimenhager and Jascha Pessin, which is what I want to talk about, and a recent paper by Ben Ovadia. In fact, so I will explain what I want to talk about in this talk is our result of myself with Kleimenhager and Pessin. This is a two-dimensional result. And I should say that just a few weeks after we had finished this preprint, Ben Ovadia sent us his paper, which in some sense is a much, much broader and much, much more comprehensive study. He deals with arbitrary dimension. He pretty much deals with the analogous result in arbitrary dimension. So because his result is so comprehensive, it seems that he probably more or less incorporates our result as well. So it's a very, really remarkable paper. The proof, however, are very different. The techniques are completely different. Ben Ovadia uses a construction of Markov partitions, which is very abstract, very general. Our proof uses a very explicit geometric construction. So I think perhaps what at least we have is that our proof is, what I hope to show you in the seminar, is that our proof is very simple and is very concrete. So I will also try to explain why it is just two-dimensional, and then maybe there are some situations in which our construction can be useful and other constructions in which Ben Ovadia's construction can be useful. So yes, so one final remark, which I will come back to, which I think is very interesting. Of course, all of these results have some specific way in which they formulate the setting and the assumptions. And I would like to say that in somehow, what I've discovered working on this subject is that there is an issue with the recurrence and how all of these papers somehow include some recurrence assumption. And I think that's a very interesting question, the extent to which these recurrence assumptions can or cannot be assumed. So I will come back to that in a little while. So let me state our result precisely. So we have, now we restrict ourselves to 2 dimensions, and we have a hyperbolic set lambda. We define a rectangle in lambda is simply a set with local product structure. So if you take 2 points in gamma, then the intersection of the local stable and unstable manifolds is a single point which also belongs to lambda. This is a completely standard definition. What it means is that it looks something like this, right? So we have basically every point in gamma has a local stable manifold and a local unstable manifold of some length, and they intersect, and gamma is the intersection of these local stable and unstable manifolds. So one comment is that there are some cases, for example, if you have an Oz of diffeomorphism, this rectangle might actually be essentially a topological disk. But in general, not in general, but usually in the cases, in the general cases we want to consider, we have to take into account the fact that it may be a Cantor set, which is one of the things that makes things very complicated. So the key definition, I will define now 3 properties of a rectangle, which are fundamental in our result. And the first is the notion of fat rectangle, which is just the same notion we had before for the fat hyperbolic set. So even though gamma is a Cantor set, and this Cantor set may have positive Lebesgue measure, the union of the stable manifolds may have the Cantor set may have 0 Lebesgue measure. The union of the local stable manifolds may have positive Lebesgue measure. In this case, we say that the rectangle is fat. Then we say that this rectangle is nice if the boundaries of these rectangles are the stable and unstable manifolds of 2 periodic points, P and Q. And finally, we say that this rectangle is recurrent if every x comes back in forward and backward time to gamma with some positive density of time, positive frequency. So these are the 3 assumptions, and I will make some remarks in the next slide about these assumptions. But first, this allows us to state our result. So this is our result for 2-dimensional diffeomorphism. So our main result is that the existence of gamma implies the existence of a Young tower. So we construct a Young tower, and I will say something again more about that with integrable return times. So a Young tower, by the results of Young, Ly-Sang-Yang introduced this notion in dynamics, this structure, and Ly-Sang-Yang proved indeed that Young tower implies the existence of an SRV measure. And what we prove also in our paper is that whenever you have an SRV measure, you also have such a rectangle gamma, which is fat, nice, and recurrent. So putting together these results, we have what we think of really as a very simple and very nice geometric characterization of SRV measures. So the main result for us interesting is this, right? That if you have a nice fat recurrent rectangle, these are fairly straightforward assumptions, then this is actually equivalent to having an SRB measure and equivalent to having a Young tower. And as a corollary, we have the equivalence of SRB measures and Young towers, which itself was not something that was obvious. Okay. Ask me any question. Lorenzo, do you see, is it possible for people to ask questions if they want? Or?
I think so. I think that everybody
Yes.
can open the microphone and make it.
Okay.
I'll try asking a question.
Yes, Kate.
So if you have your SRB measure, is the
Yes.
gamma that comes with it somehow unique, or?
No, not unique. There's lots and lots of these gammas, rectangles. I mean, in fact, I will make some comments now about these definitions, but rectangles, recurrent, if you think about it, it's just any, when you have an SRB measure, locally it has this structure pretty much everywhere, right? So given the SRB measure, it's full of rectangles with these properties. So in fact, let me make some remarks about these assumptions, and also let me be very open, very honest, so about a discussion about the relation to this, the Vienna conjecture. So in some sense, the Vienna conjecture, at least the way it's formulated, the spirit of the Vienna conjecture is just if you have a hyperbolic set, then you have an SRB measure. So what we are...
Can I make some comment?
Yes.
Maybe it's related to Keith's question.
Yes.
If you fix one of those structures, there's only one SRB measure for which almost every point in that structure belongs to the basin.
Yes, yes. I thought Keith's question was the other way around. If you have an SRB measure where the gamma was unique.
Okay.
Is this right? So if you have an SRB measure, but if you fix the gamma, because of the recurrence, is going to give rise to a single unique ergodic SRB measure. Yes, for sure. Yes. So it might not, the SRB measure might not, in some sense, cover the whole of the hyperbolic set lambda, right? So we don't know, lambda is a big hyperbolic set, gamma is a subset. Now, whether the saturation of gamma covers all of lambda, then we don't know. It's just the existence of an SRB measure. Yeah. So how much more are we assuming than just saying that lambda exists, right? So the underlying assumption is that there exists a fat hyperbolic set lambda, okay? Ideally, we'd like to prove, okay, just from that, we have an SRB measure. So we cannot do that. What we need to prove, what we need to assume is that there is a fat, nice, recurrent rectangle inside lambda, right? So what are these, how restrictive are these assumptions? Let me say that the fatness of the rectangle is not really an additional assumption at all. So if you have a fat hyperbolic set, you can at least in some sense say that fat rectangles are endemic, in the sense that, you know, unless this fat hyperbolic set is trivial or degenerate in some sense, then it will be full of fat rectangles. So this is not really an additional assumption. Whereas nice and recurrent are a little bit more delicate. So nice is the assumption that we like the least, is the least nice assumption, actually. And it is unfortunately the main reason why our result is two-dimensional. It is a technical result. We do not believe that it is, we believe that it should be, technically, we should be able to remove this result. If we could remove it, we should be able to extend our construction to higher dimensions without too many problems. When I give a sketch of the proof, I will explain why we use this nice property. And finally, the recurrence is a very interesting result. So the recurrence is used to get integrability of the return times of the Young tower. And therefore the finiteness of the measure. So we could replace the positive frequency with just infinitely many returns, and this would still give us a tower, but we would not know a first return. In fact, for those of you who know a bit about Young towers, the tower we're going to construct is a first return Young tower, which means that even if the return times are not integral, we will still get a sigma finite SRB measure. So I think this is, for me, this issue about having to assume recurrence is something that, as we were working through the proof, wait, sorry. There's some messages in writing here. Oh, no. Okay. So the recurrence is something that I'm more and more interested in, whether this recurrence, and I think pretty much all the results that exist assume some recurrence. So really, in some sense, the big, deep question, I think deep, that I am left with at the end of having completed this project, is there any way that we can show that hyperbolicity itself implies recurrence of some kind, or whether it does not. This, of course, means, it is related to questions of ergodicity is a similar question, if you have hyperbolicity of recurrence. So I think this is very interesting. I would be very interested to discuss with anyone who has any ideas in this direction. So when we look in conclusion, when we look at the difference between the statement of the Vienna conjecture that says if you have a hyperbolic set lambda, then you have an SRB measure, and what we have, I think the only thing really additional besides the niceness, which is a technical assumption which should be able to remove, I think Ben Ovadia does not have it. Somehow his construction is different and he manages not to have it. That's why his result is higher dimensional. But the recurrence, I think, is something that is not at all clear to what extent, whether in the end it's possible to have a hyperbolic set without recurrence. I think that's really the main question. And therefore, if it's possible to have a hyperbolic set that does not have an SRB measure, I think this would be the main counterexample of this conjecture. Anyway, so let me go to a sketch of the proof. As I said, I hope to convince you that our argument is relatively straightforward and conceptually simple. So this is a summary of our main result, is that if you have a nice fat recurrent rectangle, then this implies a Young tower with integrable return times. So the proof will have 4 steps, some of which are technically very involved, I have to say, but conceptually they're fairly straightforward, and I hope that I can give you a convincing proof, essentially, of the whole thing. And this will go, so I will not discuss this because I will discuss them point by point, but let me say that in terms of the way it works conceptually, it is useful to go backwards. So we're going to define something called a saturated rectangle. And in this last section, we show that if the rectangle gamma is nice, fat, recurrent, and saturated, then you kind of automatically have a first return Young tower on that rectangle. So this was also the first result that we got when we were working on this. And so we worked backwards. We realized there was this additional notion of saturated, but if our rectangle gamma that we begin with is saturated, then we were fine, but there's no reason. It'll be much too strong an assumption to assume that it's saturated. So what we needed to do is show that if we have a nice fat recurrent rectangle, we can build a saturated rectangle out of that. And this is what we do, okay? So to build this rectangle, we have the step 1. The step 1 is a very general step, and it relies on this concept that we call almost return. So let me explain carefully what this is. So we assume this is a domain that encloses our rectangle. We suppose we have some point in our rectangle gamma. This is the local stable manifold of this point. And we suppose that after some time I, this point comes back inside this domain, but it does not necessarily come back to gamma. This is a crucial point. Remember, gamma is a Cantor set in the most general setting. So this point might fall into a gap of this Cantor set, but we assume that the image of the stable manifold, which has shrunk, so at this point is fairly small, intersects the local unstable manifold of some other point y in gamma, right? And we call this an almost return to gamma because you don't quite come back. So every point has infinitely many almost returns because, of course, every real return is also an almost return, right? And so the crucial theorem, the main technical theorem of the result is the fact that almost returns imply there exists hyperbolic branch. So what is a hyperbolic branch? A hyperbolic branch is simply a strip. So the existence of a hyperbolic branch says basically that there is a stable strip. Here, by this I don't mean the Cantor set, I mean the actual, with the interior, the whole strip, vertical strip, which maps in a uniformly hyperbolic way to this unstable strip. Yeah, with some uniformly hyperbolic estimates, right? Where the uniform hyperbolicity depends on I. So if I is large, it's still uniformly hyperbolic in relation to I. This is actually a general result in hyperbolic dynamics. Those of you who know hyperbolic dynamics will recognize that this is a generalization of a well-known result of Katok. There's a very classical and very standard result of Katok that basically would apply in the case of real returns. So all the points in this rectangle, they all belong to the same regular Pearson sets. So this result of Katok would say that if you take a point x in gamma and it returns to gamma, then you'd have a hyperbolic branch. Okay, and again, just a small diversion for those of you who know a little bit of Pearson theory and Lyapunov charts, and just the way Katok's result is proved is because all the points in gamma have a Lyapunov chart of uniform size, and therefore it follows fairly easily that you get this hyperbolic branch. In this case, we don't know anything about the size of the Lyapunov chart of Fi of x, because we don't know anything about where it lands. Fi of x could fall in a gap and could have a very small Lyapunov chart. So basically how this result works is we use the fact that Fix is close to this point y in gamma, and this point has a large Lyapunov chart, and basically we iterate backwards the Lyapunov chart of y, and we iterate forwards the Lyapunov chart of x, and then both of them degenerate, but somehow in the middle we switch Lyapunov charts. So we switch Lyapunov charts, and we're able to go and to carry forward this hyperbolic branch, one Lyapunov chart, and then halfway along, we switch to the other one, which we know is large at the end. Okay, just a small parenthesis for the experts in the audience, just to give some idea. So this is technically non-trivial, but it turns out to be really interesting as a general result and a generalization. And this will be used in an important way. And in the next slide, I will explain how. Let me just make one more comment that we also have this property that if you have two branches, so if you take another point x prime inside, for example, the strip, and you look at some almost return, but not at the same time I, it may almost return, it may have an almost return at some other time, then it also has a hyperbolic branch. So it also will have a stable strip and an unstable strip. And these strips are always all nested or disjoint. And it is for this property that we use the nice property, the fact that P and Q are periodic points. So maybe I should have said that to simplify the discussion here, I'm going to assume that P and Q are fixed points. Okay, so if P and Q are periodic points, we need to take some iterate and everything is essentially the same. But let me assume here that P and Q are fixed points. So in these two assumptions, these two results are where we use the fact that we belong to a hyperbolic set lambda and the nice property of the rectangle. So let me comment again that after these two properties, we do not use either of these properties anymore. So if you could imagine trying to apply this construction to an explicit system where you do not know that you have a global lambda hyperbolic set, for example, in a situation like Henon, map kind of systems or in some other situations, you might be able to prove this theorem and this lemma in other ways, and then that will be enough, right? You can then replace the existence of a global, if you can find a rectangle that has this property that almost returns of hyperbolic branches and that the corresponding strips are nested or disjoint, then that's enough to do it. Okay, so these are the two key points in which we use the fact that we belong to a hyperbolic set lambda and that the rectangle is nice. So what is the second step? The second step is now we want to define this set gamma tilde, and we have now this collection of all these hyperbolic branches associated to all the almost returns. So it's a simple observation to show that for every I there can be at most finite number of distinct hyperbolic branches, which means that we can basically index all the hyperbolic branches in this way, where I is the return time of the branch, and then for each fixed I, you have a finite kappa j number of hyperbolic branches. So now we define the collection of all hyperbolic branches that are generated by all these almost returns of every point, right? So every point has lots, infinitely many almost returns. Each one of these at different values of I generates a hyperbolic branch. So notice that, as I said before, these hyperbolic branches have this nested or disjoint property, but they may be nested, they're not disjoint, right? They're nested or disjoint, and every x in gamma is actually containing infinitely many of these nested slips, because for each almost return of this point, it is contained in some nested sequence of slips. So the picture we have is a kind of fairly complicated horseshoe with infinitely many branches. But it's not just infinitely many branches, because the stable slips corresponding to these branches are not all disjoint. They are also nested. Okay, so what we want to define, however, a little bit like the usual horseshoes, is we want to define the maximal invariant set of this horseshoe. So we want to define the meaning of the maximal invariant set. And of course, the maximal invariant set depends. So what do we mean by an invariant set? We mean points that stay forever inside the stable slips, right? Just like you do in a regular horseshoe. Now, if you choose a point X, because it's got infinitely many nested slips, then you have an infinite number of choices for the iterate that you choose for that point. And it may be that if you iterate it for some value I, according to one of the slips it belongs, then its image falls outside. So you lose that point as in the maximal invariant set because it falls outside these stable slips. But if you choose a different iterate, then it falls inside. Okay? So we need here a we define in kind of fairly abstract way this maximal invariant set, and it is those sets that have what we call a hyperbolic sequence, so a sequence of hyperbolic slips with the properties that for each positive and negative m respectively, the image under X under this iterate falls inside a stable slip. So what this really means is that after you iterate I0 times, then it falls inside the stable slip CS I1J1, right? And then because you're inside CS I1J1, you apply I1 times. And then when you apply I0 plus I1 times, it will fall in C hat as I2J2 and so on. Okay, so this would need a little bit of digesting, but basically it's those points that for a suitable choice of iterates always stay inside the stable state. So it's really a very natural generalization of what you do for regular horseshoes when you talk about the maximal invariant set. Okay, and it turns out that this maximal invariant set has some properties, so it's fairly easy to see that this is a rectangle in the sense that it has stable and unstable locals. Every point, there might be some new points, some points that are not in the original rectangle, but it is a rectangle because they all have stable and unstable local manifolds of the same length. It contains the original gamma, because of course every point in gamma satisfies this property because it has an infinite number of returns. So in particular, if gamma is fat, then gamma tilde is also fat. And it has a very interesting kind of closure property in the sense that every almost return to gamma tilde is actually a return. So it does not have any almost returns that are not returns. It's a bit like you've filled in all the slots. You've included all the points that you should have included from the beginning, right? And not only that, but now you have a new rectangle and you can talk about the set of its own hyperbolic branches, and the set of hyperbolic branches connected to these returns is exactly the same as the original set of hyperbolic branches for the almost returns of gamma. So in some sense, this gamma tilde is the rectangle that we should have had from the beginning, right? But we didn't know we had, or we couldn't assume we had. So this is the rectangle that contains all the points that it should contain. And now we want to show that this rectangle has the saturated property that I defined previously. So since it's a rectangle, we can now just introduce some notation. We write CS is the union of all the stable leaves of the points in the rectangle. CU is the union of all the unstable leaves. Gamma tilde is the intersection of this. Right? This is just the rectangle is like this. And then we can define the following objects. So this is a crucial definition here. So let me show you this picture to say, understand this definition. So we have a hyperbolic branch, right? This hyperbolic branch maps C hat Sij, which is this, to C hat Uj. And as you can see, what we're doing here is we're taking C hat Uij, which is this horizontal strip, the unstable strip, and we're intersecting it with all the stable leaves associated to the rectangle, right? So that's what this, I don't know if you can see my cursor here, actually. This here.
We can see, you can go.
Yes. Okay, you can see the cursor. So, so this is a union of stable leaves inside these unstable strips, right? And now we take f to the minus I. So f to the minus I of this unstable strip is a stable strip, is a full height stable strip. So each of these stable curves, it maps to a full length stable curve, right? And this is exactly the definition of CSIJ. So CSIJ is the union of all these stable curves that you get by pulling back this. Okay. And the same thing for CU in the other direction. So for CU, you take all the unstable curves here and you pull them back and you take this. So one important subtle observation, which is not particularly relevant, but I think it's important to keep this in mind, is that there may be some other stable curves inside this region, okay? There may be. These are stable curves which at time I fall into the gaps, right? So we do not see them. Here we have taken all the stable curves that we pull back from the stable curves of gamma tilde, okay? And actually, what we're mostly interested to know is whether by pulling this back, we have added any new curves or whether we already had all those curves. So now I need to get it, okay? So the definition of saturated is the following, is that gamma tilde is saturated if, so now there is a, yes. So if all these curves that you pull back by the hyperbolic branch, they already belonged to CS. It's a very natural definition. It's saying that saturated, the idea of saturated is meant to convey the fact that you already have all the points that you really need, okay? And clearly, if you're pulling back all the stable curves here, then the stable curves, the long stable curves you get here should naturally belong to your set. Okay, so this is the definition of saturated. And the main result we have here, indeed, is that gamma tilde is saturated. So when we define gamma tilde by the definition I gave in the previous slide, then it turns out that it is saturated. So you have indeed added all the points that you had. So this leaves us now with the final step, which is to show that saturated rectangles have Young towers. So I've not defined Young towers, and I think I will, rather than define it, I will now give a sequence of statements that essentially give the structure of a Young tower, because otherwise, anyway, it does, if you don't know what it is, it's a bit confusing. So let me basically recap what the result of this section is. Kind of an independent result. It's saying that if you have a nice, fat, recurrent, and saturated rectangle, which is the property that we were missing from the previous rectangle, then it supports a first return Young tower with integrable return times. So in this case, this rectangle is exactly the base of the tower. Or another way to say this is that if you just take the first return map from this rectangle to itself, just the first return map, then miraculously it has the structure of a Young tower, which is very non-trivial, because a Young tower is a very non-trivial structure. If you just take the first return map blindly, there's no reason to have the structure, but the saturation property guarantees that. So I cannot give a full proof, but this part maybe will be a little bit technical, but basically what we do is we have those sets that we had before, these CSIJ and CUIJ. If you remember, the CSIJ is a union of stable leaves, okay? So we now intersect it with CU, and we end up with a Cantor set. And this Cantor set is in gamma tilde. I've kind of dropped the gamma tilde here, right? Because I'm just assuming now gamma is a saturated rectangle, but we use the same notation. So this is now a Cantor set, which is obtained in this, and this is also a Cantor set. And the next few results more or less follow. They're not intuitively obvious, but they more or less follow by calculation. They don't need any real big argument. And the first observation is that they map one to each other, which is not surprising, but is not trivial, because they're not defined in that way. Actually, they're defined kind of independently. And also, the collection of sets gamma Sij are themselves pairwise nested or disjoint, and the gamma Uij are also pairwise nested or disjoint, which again does not actually follow immediately from the fact that our strips that we use in the construction of pairs are pairwise nested or disjoint. Although of course it does follow from that property, but it's not a kind of trivial consequence, but still they have this property. So these are Cantor sets, but they're pairwise nested or disjoint. They're not disjoint. Okay, of course, for a Young tower, we need the disjoint set, but at this point, it is very natural. There's a very natural way to choose. Since they're nested or disjoint, we can define a partial order by inclusion, and we can just define a maximal family of this partial order. So each element of this maximal family is not included in any other set, and they're all disjoint, which means none of these two elements of this maximal family are nested, so they must be disjoint. So we now have a disjoint family, which covers all of gamma, because this families cover all of gamma, and we have a maximal family. And then we prove the lemma simply that if you now take any element of this maximal family and you take a point in this element, then every point returns to gamma as its first return at time I, which means exactly that every point returns at the same time I, and it's the first return for every point, and it is exactly equal to gamma uj, right? And as I said before, I mean, it's fairly straightforward that these gamma Sij's are the partition of gamma, and the PUs are also partition of gamma. So we have, this can be used almost as a definition of a topological structure of the first return Young tower. This is what I call. So we now have our rectangle. This rectangle is partitioned into stable sets. These have exactly, because of this structure here, these have the structure that Lysa and Young calls S subsets of the rectangle, and these are U subsets of the rectangle, and they map to each other. Okay, so this is the topological structure, and then the full Young tower also satisfies some analytic properties, some hyperbolicity, and some bounded distortion estimates, which actually come from the estimates about the hyperbolic branches. So we know that each of these is contained inside a hyperbolic branch, and then it is relatively elementary to do that. And then we use the integrability of the return times comes from the recurrence conditions. So this was, in fact, a very nice. I would like to thank two people who are in the audience, actually. So Dima Dolgopiat, some time ago, pointed out that we needed to prove integrability, even though it was a first return time map, something that somehow we had kind of got distracted on. And Wilton showed us a very nice estimate that shows that if you have positive frequency of returns, then you automatically get the integrability. And so this is why we need to get the integrability. And so this gives the Young tower, and this gives the SRB measure, and this completes the proof. So I think we are precisely in time. So thank you very much, everybody. This is it. Thank you very much.
Well, now we start questions, please. I think that it's not possible to see it's only the people, but we can start. There is some questions or comments, remarks.
Small question.
Yes, please,
If
Dina.
you have, so one of your assumption is recurrence. If you have some quantitative estimates on recurrence, can you get some stronger results about properties of your SRB measures?
Yes, I think the recurrence, and now actually we talked about this with Vaughn and Yasha, and we have in the paper actually some results in this direction. Yes, we do. If we assume the recurrence to be exponential, we get exponential tail, I believe. Yes. Yes. Although, and Vaughn, sorry, this part of the paper I've not looked at for quite a while. Maybe Vaughn remembers more precisely, but we do have that, yes.
More questions?
I can follow up what Stefano said to just say that, yes, if you take the set of points which have not returned by a particular time, and you know that the measure of this set decays exponentially, then you have an exponential tail estimate on the tower.
Yes. But it kind of, to me, to be honest, since we're having a discussion here, it kind of felt as though, assuming exponential recurrence to begin with is kind of, I don't know, maybe Vaughn said there were some examples in which this was natural to assume that. It seemed to me that it would be nice to get some estimates. I mean, okay, so the question that I have thought of for a long time, and let me take this opportunity to put it there, is kind of the converse. Suppose the SRB measure has exponential decay of correlations, right? Then can we get exponential tail of the return times for the Young tower? I think in some sense this is a more interesting. So, or can we get, somehow from the decay of correlation, the currents? Because if we assume the currents to begin with, then it's kind of natural that you also get the estimates on the tail. But it's true, it does show that our construction is very explicit in that.
More comments? Questions? Well, if not, let me just finish. Well, we will think about rescheduling the meeting for earlier. I don't know what is the most convenient time. Maybe I don't know. I have no idea. Maybe to try to.
I think maybe some like 10 o'clock or 11 o'clock. 11 o'clock should be fine, probably.
11 o'clock, do you mean Brazilian time?
Brazilian time, maybe 11
Brazilian
o'clock. I don't know. You can.
Europe
You
is
can,
+5. I don't know what is the time in China.
yes, so that's what you need to ask. You need to ask people in Beijing or in Shenzhen. And,
Well, I will ask the other people about
yes.
and then well, try to get a new schedule.
It's
Yes.
4:40 a.m. in Beijing now.
Is that,
I guess
who's,
it's Adriana Alus. So
uh-huh.
if you do a meeting at 11 a.m., it would be 10 p.m. in Beijing.
You think that 11 is okay? 11 in Brazil.
Yeah, the earlier the better, because
Okay,
like, if we do it, for example, at 10, then it would be 9 p.m. in Beijing.
Then I will risk, if Pedro Duarte agrees, I will reschedule his talk for 11 a.m. Brazilian time. That is +4 in United Kingdom, +5 in Europe. I don't know the state, that depends in the area. And well, let me thank you for participating. And thanks again, Stefano, for his talk.
Yeah, I want to say something, Lorenzo.
Yes.
So since I don't know Zoom, I realized that anything I said was not transmitted because my unmute button wasn't pushed.
Uh-huh.
But all I had, I was going to record the whole business, and I had to request from you the permission to do that. So I kept saying, all you have to do is find somewhere where you give me permission. Of course, you didn't hear it.
Well,
So but there's somewhere on the person who invites the meeting, if someone else requests to record, permission to record, somewhere you have to say okay. And then I presume it will be recorded.
I think, well, I know I am very unfamiliar with the Zoom. I guess they record the talk.
Oh, you did? You think so? Okay.
I think so. At least I guess that everything was recorded. I don't know. The next problem is where we should put maybe we can try to organize this by ICTP, if Stefano agrees. Do you agree, Stefano?
What do you mean?
Well, to have the records of the talk. Well,
yes. You mean to have a repository, to have a site someplace where we can put them, yes?
I recorded the talk, but I don't know what to do with this.
Yes, well, we could put it on YouTube. Put them on YouTube. If you want, I can put them on on YouTube, and we can talk about this. Yeah.
Okay, we can think about this later. More comments?
Okay.
No, I have a suggestion.
Yes,
Hey.
please.
No, next time everyone should take some. First of all, thanks to Lorenzo to organize this thing.
There is some microphone.
I don't know who is with the microphone.
There is some background noise somewhere.
Okay,
Yeah,
now
now
it's okay.
Okay. First, thanks Lorenzo for organizing this virtual meeting. My suggestion for the next time is everyone take some glass of wine just to
11 a.m. They say too early.
make a brindis after the talking, following our
Very good, Zezé. Great.
a virtual brindis to everyone.
Okay, then
I don't have just water here.
For 6 is too early. You know, I cannot contribute to outreach the community.
Okay? And then everyone with
you're killing me, Daniel.
money or whatever.
Okay, Zezé, I agree with you. Let's do it.
Okay.
Oh my God.
Well, let's start again, Stefano.
Wow, thank you.
Tchau, gente.
Ciao.
Ciao,
Ciao,
everyone.
Ciao, todo
Ciao.
mundo.
Ciao. Thank you,
Ciao.
everybody.
Ciao.
Thank you very
Ciao,
much.
ciao, ciao.
Thank you. Thank you, Stefano. Thank you.